time is about right to start. I hope we can hear my mask out. Okay, yeah, first of all, welcome you all here. And before we start, I should remind you that there's no internet, and no recording, and no video except that. Okay, and please be careful not to put anything in front of the projector. May damage the projector. That will cause unnecessary complication. All right, and I think all students know rules are probably better than many of the jurors. So I'm not repeat that. Before we start, I will juries. First of all, Professor Paul from Donghua University.
Good morning, everybody.
Yeah, and Professor Ke from National Taiwan University.
Hi.
And Dr. 朱万生 from Taiwan 科学教育。And Professor Guan Qishan from Taiwan University. And my name is Guo Zelai from Academia Sinica. Okay, so let's start with the juries, and I'd like to ask the captains of each team to introduce your team members. And we start from the opponent team. Who is the captain?
We are Mark Shashang from Junior High School, and I'm captain. My name is Lin Qingzhe, and this is our teammate, Nan Kai Wang Yuanhua, 曾亚人叶新友。Thank you.
Yeah, perhaps you can slow down a little bit. I think with the mask it's difficult to hear clearly.
Dear judges and fellow competitors, I'm Chen Xingwei, the leader of the Huasian. So this is Dong Yaoxian, Su Yuan, Xu Yiyou, and he's still in battle. We got a teammate still in battle.
Huh?
We got still one more teammate, but he's in the back.
Oh, okay. I think with the mask on, we need to make our voice, the volume slightly bigger, okay, than normal. Otherwise, it's hard to hear. Okay. All right. Yeah, I think we can wait a couple of seconds before the last team member goes up more. Okay, but once the game starts, then we have to observe the time. Okay. Okay. Ready. 这一组刚刚上色，中间的那个就上色。Yeah, we wait one more minute before the last team member. Everyone is here. I think we will start with round one. Okay. So the opponent will challenge the reporter.
6, that is for power.
Number 6.
Yes, it's for power. You accept your challenge.
Okay, so the challenge is accepted. Let me remind you when you speak, you got to make sure your volume is big enough with the last stop. Now, the report has 5 minutes of what I'm doing.
coaches and moving opponents. I'm a reporter for Team Palace and D121 tennis court Palace. So this is the outline of our presentation. So I'll start with a statement which will state our focus on this topic, and also describe the phenomenon, and also the theory, the model we use to calculate this problem, and also the experiment we conduct, and the summary of our experiment, and finally the conclusion that should then give the answer to the structural limits. So the problem statement states that build a tower by stacking tennis balls using 3 balls per layer and a single ball on top. Investigate the structural limits and the stability of such a tower. How does the structure change when more than 3 balls per each layer and a suitable number of balls on the top layer are used? So that's the first part of the problem stated. We have to build a tower with 3 balls per layer, which you can see in the demonstration. There are 3 balls per layer and one ball on top. And we believe that the focus should be the angle between the contact point, which directly relate to the structural limits, and also the height of the limits, which I will further discuss later. And also the third one is the different balls per layer. So here's a demonstration of the tower, of the first tower, and we name it 3n plus 1, which means n makes the layer of 3 balls, which, like for this demonstration, there are 2 layers, and also like top layer with 1 ball. And if you see from the top, you can see you can see the ball, the top ball was and 3 ball having like in a triangle, which is the ideal shape we expect. So here's a theoretical model we use to calculate this problem. So we first started with a simplified problem, which only has a layer of 3 balls and balls on the top. So as the free body diagram shows, this line is the center. It's the line that connect to center. And so as you can see, the normal force exerted by the top layer is pointing directly to the center of this ball, and also the normal force from the ground. And because it's just a 2-dimensional graph, this friction is not necessary at this way. It might go into the spring or outside the spring, which we will discuss later. And so does the friction by the ground. So this formula is what we use to calculate this problem. So first, because in order to make this tower stable, it must accomplish 2 criteria. First is the force equilibrium and also the torque equilibrium. So the first one is the force equilibrium. So as you can see, M1, the first equation is the vertical forces, and so this component will create a force equilibrium. And the next is the horizontal force, which will also create an equilibrium. And then the torque equilibrium. But at this equation, we only calculate the magnitude. We do not concern about the direction first. And so there's a ball on top, and there are 3 contact points with the bottom layer. So the mass, the weight of the top layer should be evenly distributed to the 3 ball to create the biggest stability. Therefore, mg equals 3 times the vertical force. And then we can conclude that the friction, because this 2 friction should be the same, has become this value. And so we plot that value back to the force to cause, which will give us the minimal static friction it requires. So as you can see, the friction between the coefficient of the friction between the ball and the ground should be 1/4 of the friction between the balls. And so for a ideal shape, the tetrahedral, the cosine theta equals 1 over root 3, which yield the two coefficient of friction. But this is just for a first layer. And then now we're discussing a more complex model. So this is a 2-layer, there's a 3-layer, and we discussed the bottom 2 layer. Because as the picture here shows, you have to do it this way. This ball is slightly out of the screen, and this one slightly into the screen. And then the bottom layer will be 1, 2, 3. So this ball corresponds to that ball, and the green one corresponds to this one. And then the friction between them will create this formula, and because it has a different angle, so the formula looks different. And then for the horizontal equilibrium for the green ball, we can yield this formula, and for the vertical one, we can yield another formula, which looks pretty complex. And then so we can calculate the friction force from here. And this too is just the approximate value for the ball that n equals 2, because there's like 105 degree outward, shifted outward. So yeah, that's the value of what we use. And then we divide the friction over the normal force, we can yield the friction coefficient of friction required between the ground and the balls. So using these two models, we can calculate the coefficient required for each layer. And as you can see, the sine theta, sine phi, this one I will explain later, because we have to discover another phenomenon which I will explain later. So assume that when sine phi is smaller than 0.6, the tennis ball will not create a force equilibrium, therefore it will fall down. So this value is between 12 and 13. Therefore, the structure limits of this ball is of this tower is 12 layer. So here's our experiments. We have numerous tennis ball and a scaffold to pile up the tennis ball. And then we also have to check if our theory fit the model. So we have to measure the coefficient between the tennis ball. And as you can see, it looks pretty funny because we cut the tennis ball into pieces, and we place two pieces of the tennis ball together, and we use different ways to test its coefficient. So as you can see, the maximum we create is 6 layers, which contradicts with what I said, the 12 layers. And coefficient experiments, as you can see, we have tested 4 different kinds of weights. But as you can see, the coefficient actually drops. And this one, but we cannot find any standard formula to calculate the coefficient difference. Therefore, we can only plot this. This dots. Oh, no, sorry. We actually use five data. And that's what's here. And we can only fit a line which yield a 0.993 r squared. So we believe that this should be the line of the coefficients difference. So as a result, we plot that into consideration, the coefficient force difference into consideration, and which shows that the maximum of this is 6 layers. And the next experiment is we have 7 balls on a ball layer, 6 balls on the second layer, and 3 balls on the top layer. And this is the maximum we did. So for this one, n equals 4. And using the same model this time, as you can see, it's actually many 3 balls put it together, which can be kind of using the same theory, same model, but more complex calculation. And we yield when we yield different sine phi value, which looks like this, and which shows that 5 layer is the maximum. And for our summary, the friction, it is the friction force that hit the power state equilibrium. And however, the coefficient of friction increase when normal force increase. Therefore, there is actually a structural limit to it. And then, however, in the real world, we can only pile up to 6 layers, and for another kind of tower, it's 5 layers. And there's another phenomenon that we can qualify, which is the deformation of the tennis balls. And we believe that that is another factor that causes us to not yielding the highest limits, because this, when a tennis ball deforms, it will actually change the contact angle, which is very hard to qualify. And a conclusion, the theoretical model deals with structural limits of 13 layers, but the real model is only 6 layers. And it's due to the change of coefficient of friction. And also, the reason for collapsing is the angle. And we believe it is from, when it's collapsing, it's from the layer that could not support the friction it required. So, for example, if you pile out 7 layers, and the limit is 6 layers, so therefore it will start to collapse at the bottom layer and between the second bottom layer. And here's our reference, and it's in here.
So what is your maximum layer of the view? Layer, right?
Do you mean the three layers?
How many layers did you build with your tower?
For which tower?
Okay, jump on to the next question. Do you find the boundary friction? Boundary friction, you already said the friction is the most important part. Did you find the boundary friction?
Go to the sorry. Here. This is the formula.
And did you agree that with higher the tower, the less friction is between the balls?
The less friction is
Yeah, the less friction is between the balls.
between the balls.
Yeah, between the balls.
Between each layers, the friction is different. So which layer?
Okay, thank you. And did you consider your ball as a rigid body?
Oh, no.
In your theory?
Oh, yeah. In the theory, it does, but not.
And according to the problem statement, you have to test the structural limits and the stability, and did you do any stability tests of the tower?
Yeah, we actually observed how it collapsed. And
Okay,
just
we will discuss this more in the discussion time. And do you think there is force between the gap of the balls on the same layer?
if it's contacting, there should be normal force, but as I say, the angle will change, so it will not.
And according to the problem statement, you have to change different layer, different ball number on the same layer to do the experiment.
As I show later, there's a 6 plus 7.
Okay, and so do you think so more layer on each layer, do you think it is more stable or a lot more stable?
You mean when the height goes up?
I mean when the number of balls on each layer.
But it's actually not going
Time
to be
is
more
up.
stable.
Okay.
The point is luminance to prevent. start anytime. The opponent takes the floor maximum 4 minutes.
Honorable juries and fellow competitors, I'm Chen Nankai from Jingcheng High School, Park Cha-Cha, and today I'll be the opponent for problem 6, tennis ball tower. So problem statement is like this. Build the tower by stacking tennis ball using 3 poles per layer and a single ball on top. To investigate how the structural limits and the stability of such a tower, and how does the situation change when more than 3 balls per layer each layer and a suitable number of the balls on the top layer are used. So for this problem, we think it is very important to investigate the structural limits, which the report has done, but they lack the stability test of their tower. So I will discuss with them in this part more. So the main focus should be the theoretical prediction for the structural limits, and second, to quantify the stability of the tower. And here is the structure of the reporter's problem. So first, they show the observation photo with 6-layer tennis ball tower. But I want to discuss with them if it is possible to build more than 6 towers in a discussion time. Then for the theoretical model, they use force equilibrium and torque equilibrium to analyze the force. Then for the setup, they explain how it works by stacking the balls, but they didn't tell us what is used for the scaffold, and maybe I'll discuss more with them in the discussion time. And with the experiment, they did different layers on each layer, which is problem statement to us to do, and different tennis ball in the layer. And for their conclusion, they do in theoretical, the maximum limit is 13 layers, and it is reasonable for collapse are the angle and the top of the ball. And here are some strong and weak points for the reporter. Firstly, they have a clear introduction to a problem, and they give us an observation photo with 6 towers, and they have a clear explaining their theory very well. And third, they experiment to verify the theory regarding the torque and the maximum layer. And for the weak points, we think that they need to address the problem with the stability of power, which they didn't do in the experiment. And they have no theoretical consideration in different normal force that cause that is on with the more layer on each top on each tennis ball tower, which the opponent think that the normal force will become lower, and the friction will also become lower the higher the tower goes on. And third, they lack investigation on the stability and different structures. And fourth, they have inadequate experimental verification on the boundary condition of the friction. And here are some points I want to discuss later in the discussion time. Which is first, we observed a 6-layer, and I want to discuss how they could minimize the deviation and build more towers, which is the problem statement. And then for experimental setup, I want to ask them the tolerance of a tennis ball, like the size and the mass, and what is used for a scaffold. So how they structure the tower, and what is the tower look like. And third, I will discuss them about the free body diagram and how the tower is stabilized, and the friction and normal force and gravity, which the opponent think it is very important in this problem, and the torque balance. So other parameters I would also like to include in this discussion. Firstly is the layer of towers, number of balls tower, and we could use collision to test the stability, and use earthquake simulator to test the stability.
You may remove your mask. And the discussion.
Can you go to the piece of your experiment setup? So first I want to know how you build your tower.
May I control?
Oh, okay.
So on the internet, we actually see a Facebook shows how to build such a tower. They use a column around the tennis ball tower.
Oh,
And they tie all the balls between them. And from getting from their inspiration, we created a triangle that will stabilize the ball before we took off the scaffold. So the ball will be between them. And which can, I cannot draw it precisely, but actually kind of compress them together.
Yeah, okay, so the report, so the opponent thinks that the report did this way is because they want to minimize the gap between the tennis ball. Is this correct?
Yeah, that's correct. Because that will fit the theoretical model.
So after you stack this up, you have to put one ball on top, right?
Yeah, true.
And if you don't put that ball up, it will completely collapse.
Yeah, because the
Okay, can you explain how it is important for the top ball?
so for the opponent's question, he asked the top link. So as my demonstration picture shows, can you show the one that no, not this one. More. Oh, yeah, this one. So as you can see, the top layer's center of mass actually shift from the contact point, which will cause torque unequilibrium. So you can see, gravity is here, and the bottom layer is here. So it will cause a torque this way. Therefore, you need something to hold it on, to hold it stable. So you need a top ball. And as I shown in my theoretical model,
Yeah, so it is a friction.
yeah, it's the
causes
friction that balances the ball.
balance moment.
Yeah.
Okay, and because you are discussing your theory only with like 2 layers, so do you think if natural? So if there is like there's infinite layer of power, and we consider like this 2 layer over here, and then it's an infinite tall tower. So do you think the friction between here and here is the same?
No.
Yeah,
It won't be the same as this formula shows. You have to take an n into consideration,
Yeah.
which means n equals to, in your scenario, means the layer on top of it. And as you can see, it's the same scenario as the bottom layer.
Yeah, and we also have to consider the center of mass of the towers. Yeah, so
I see where you are going. You
yeah, because
want to
the
discuss
center of mass is because it is like the vertical tower, so the center of mass will directly point to the center of the lower ball. Do you agree?
sorry, what do you mean by center of mass and 120%?
I mean the normal force contacting the next layer of the ball will not directly point to the
So
center of mass.
So are you saying that in a tall tower,
Yeah.
the normal force will not be on this direction?
Yeah.
Is that what you're asking?
Yeah.
Well, actually, it's not true. It should be.
Okay, let me ask you, in your experiment, did you observe the contact point or contact plane?
So as my theoretical model stated, the model only consider when the ball are contacting each other.
Yeah.
However, sine phi actually corresponds to when the 2 balls are not contacting each other and they have a different phi between their angle.
So the following question is, do you think that it is a contact area over here in your experiment? Do you think it is a contact area?
You mean in the real world?
Yeah, in the real world.
I have to tell you that only in the first 2 layers
Yeah.
there are contacts.
Okay.
When it goes further on,
It is a contact plane, right?
yeah, contact plane.
Yeah, contact plane. So the opponent thinks that the balance moment before the higher the tower goes up, you have to consider the center, the torque of the normal force. Do you agree? Because it won't pass the center of the ball. Do you agree with this theoretical model?
I don't actually get which contact plane are you asking?
Uh,
Are you asking the contact plane between the same layer or the bottom layer?
The bottom layer. So
Well,
you know, like this. So it is not directly, but through the center, it's like maybe over
have the equipment for such testing, but if we do have the equipment, I would like to test it on a shaking crane.
Oh yeah, like your earthquake simulator.
Like an earthquake simulator.
Okay, so for the opponent agrees to the reporter that the earthquake simulator could be used to test the stability of the tower. So you change amplitude and frequency and test the different stability of the tower. Yeah, and so the opponent also think that you could collide a tennis ball with the tower. Do you agree with my view?
Collide tennis ball with the tower.
Yeah,
So,
collide tennis ball. The bottom layer of the tower. Do you think this is also a way to test the stability of the tower?
it should be, when you when you exert another force into it, it would definitely break the force balance.
Yeah. So you can test the stability. Do you agree?
I think it could be an extra experiment
Yeah.
on top of the earthquake simulator.
Oh, okay. So the problem statement also asks us what would happen if the ball is like 4 layers each, like there are four balls on each layer. On that four layers each tower, how do you think the force would? Do you think it will be more unstable? Stable?
It should be more unstable because for a 4-ball scenario, it must be, I just drew the standard max. So here's a 4-ball, and another 4-ball should be like this, and there should be a ball on the top. Right?
Yeah.
So for this scenario, the top, the force down is mg, and there are 4 contact points. Therefore, the normal force only equals to 4 over mg.
Oh yeah, the opponent has it, yeah. And the other point that I would like to add on is the angle. So if there are four tower on each layer, the angle will be more bigger. So there is a bigger horizontal component that will cause the torque. So the tower becomes more stable. The more layer on each layer, more ball on each layer. Can you agree with me?
Be more stable.
Be more unstable.
Or more unstable. Yeah.
And also, I want to also ask more about the experiment. So, what is the tolerance of the ball?
Tolerance, you mean
That the deviation between the balls?
they actually change
Yeah.
because as you see, the angle change will cause a greater normal force, right? And greater normal force.
The question of the opponent is your experiment. So
I'm answering you using this. So as the angle increases, the normal force will increase. And as the normal force increase, it will create more friction force, which can correspond to a torque equilibrium.
Yeah, so do you think that the difference between each ball, because it is very hard to control the same maximum, so it will cause a deviation to a structure.
When the balls are different, it might cause a
Okay, time is up. Upon the summarize the discussion.
Okay, so in the discussion time with the reporter, first we discussed how they structure the tower with the scaffold, and the opponent think that they try to minimize the gap between each tower because the contact of the ball is crucial, and it will cause more stability if the ball is like more contact with each other. And we also discussed about how we could test the stability of the tower, which is the problem statement that we could use the earthquake simulator to change like the amplitude and frequency, and we can also use the collision of the ball to impact the tower. And then we also discussed how different number of balls on each layer would affect the stability of the tower, and we have the same idea that the more ball on each layer, it will be more unstable. And also we think that the difference of each ball is the main reason that we can build a tower to higher. Okay, thank you.
Thank you. Let's move on to the questions from the reviewers to the reporter.
Okay, good evening, judges and board opponents. My first question is for the reporter. So, do you think that in your diagram you stated that the coefficient of friction between the balls and the table is changing in a logarithmic manner due to normal force? Do you think that it is a normal phenomenon?
I mean, this
Yeah,
picture.
exactly.
This graph is actually the coefficient of friction between the tennis ball.
So do you believe that if it is affected by normal force, if the normal force is larger, the coefficient of friction is lower, do you think that is a normal phenomenon?
We actually came out some explanation for it. So there are some fur on the tennis balls.
Okay, so you think that further affects this phenomenon?
Yeah.
Thank you. And what do you think?
Yeah, I agree with the reporter.
You think that fur on the tennis ball will affect the coefficient of friction to make it less if the normal force is larger, correct?
Yes.
Now the next question, do you think that the table's material will affect the phenomenon?
Yeah, true, because there are required coefficient of friction between the ball and the rim.
And what do you think?
Yeah, I agree with it, but I think the main friction that causes stability is the friction between the balls.
Okay, thank you. And the next question is, you stated that using a earthquake simulator, you can know the structural limit of the tower. But why, by using a earthquake simulator, you can know the structural limit or the structural stability of the tower? What is the reason?
Because when the bottom layer shift sideways, it will cause a unbalance, like on the top, the ball on top, the center of mass will shift it away from the bottom, which will cause a torque onto the top of the ball, which will cause instability.
And what do you think, Nicholas?
Yeah, I agree with the format.
So you all agree with the report? Okay, thank you. And the next question is, you assume that if the tower sine phi is smaller than 0.6, the tower will collapse. And why do you assume that? Because we can see that in your experiment, right?
Because the angle corresponds to the friction required, the torque required to maintain the stability. And if you are curious, there's actually a calculation on this topic, and the result is between 12 to 13, and as you can see, there's a thin gap.
Okay, thank you. And the next question is, do you think that the elastic properties of the tennis ball will affect the phenomenon?
Definitely.
So why did you do it?
Because we cannot quantify.
Okay, thank you.
Okay, that is all. And the review was 2 minutes.
I would like to start my presentation. I am the reviewer from Team Latashin. I'm at Zeus. The cover statement states that build a cover second tennis ball using 3 balls per layer and a single ball on top. Investigate the structural limits and the stability of such a tower, and so on. Their focus on the tower is the limit of the tower, the angle between counterpoint, and the different balls per layer. But the reviewers thought that we should focus more on the material's elastic characteristics of the ball. especially tennis ball, as the conversation says. Now, the bottom amount is a number of tennis ball can be stacked on your tower. The theory they use is the static equilibrium and the changing of coefficient of friction. And the experiment they use is stack tennis balls with different configurations. Their strengths are clear demonstration of phenomena, clear schematic diagrams, but their weaknesses are their lack of quantitative result. They made unrealistic assumptions in theory. They didn't elaborate on the reason why coefficient of friction changes due to normal force. Their overload of the elastic properties of the tennis balls. Now, for opponent, they have a clear presentation. They discuss many plausible parameters, but their weaknesses are they did not elaborate on theoretical deviations and they did not notice the elastic properties of the tennis balls. Now, for the discussion, the home asks how did you build a tower, the course they use secondary as support. The viewer has no comment on that. The next discussion, what is the situation on the top layer? The viewer said the equilibrium. The viewer think that there are more elements affecting the structure, such as the elastic properties of the tennis ball and the deformation of the tennis ball due to normal force. They separate. The next question is the force on the ball should not go through the center point of the ball. The reporter says that is not true, but the reviewer agrees with the opponent. The force diagram should consider the deformation of the tennis ball due to the force they suffer. The next one is, what ways can we know the stability of the tower using a tennis collision? The reviewer says we don't have the equipment, but if they had the equipment, they could use an earthquake simulator. So they could have done so. The reviewer agrees with the opponent that they should test the stability of the tower, just like the common sense says. And except using a earthquake simulator, because since earthquake simulator only acknowledge the bottom surface of the structure, but the side structure of the structure is important too. So maybe using a collision device is a good way. Now the question is, the first one is the definition of stability. Since this question statement states that we should find the structural stability, we should find the stability of the tower, and both the opponent and the reviewer didn't mention the definition of stability. So what is stable? What kind of tower is stable? What kind of situation can make the tower stable? And the next one is the logarithmic relation between coefficient of friction and normal force. And reviewers think that it is not normal to have such a relation between the two. And the next one is, will the surface of the table influence, which the reporter and the reporter didn't elaborate on that, and the opponent didn't mention that. The next one is the internal stress, strain, or bending moment of the system is that due to because it is not a rigid body, it is a body that with some elastic properties. So when it is forced, it will cause some internal strains or strain in the body, and we think that it has to be considered for furthermore experience. And the next one is the reviewer's suggestion for analyzing the internal stress or strain and the structure is by using a analysis method called finite element analysis, which is a method that can analyze the inside situation of a non-rigid body. The next one is what is the optimal structure of the tallest tower, which they didn't mention. And the final one is their persuasive explanation of significant deviation from theory, which is the 12 layer and 36 layer. Thank you, everyone.
Before that, you
On understand both the opponents on the board. And so for a concluding remark, I want to clarify some point. So regarding the stability of the stability perspective of the problem, we think more probable interpretation of stability is to what point will the tennis ball collapse, which is illustrated in our presentation. That was what we initially thought, but I also want to send to the reviewer and the opponent that suggests different way to test the stability. And also regarding the reviewer's question, because of this, the elastic quality of the ball will cause deformation of the ball, and we cannot conduct such an experiment because first it is hard to observe, and also it's hard to calculate into the theory of into the theoretical model we use. So, and as I said that, because this might be one of the main reasons that we cannot reach such the theoretical limits. And also the opponent discussed different number of the ball of the tennis ball tower and the relationship between the angle of the torque, which I find valuable. And the opponent suggests to use our simulator to calculate stability, which we hope to conduct in the future. And also, I think the reviewer's suggestion of that method, I will would like to look it up in the future and also try to perfect our experiments. And yeah, I guess that's it.
And now, the jurors, any questions? Any questions from the question?
Is it possible that you stack the board layer by layer and say the stable at 7th layer, for example, but maybe at 20th layer not stable? Or start before.
Everyone's clear about the question, right? Seven not stable is 20 or higher than stable.
The reviewer believes that it is possible because of the deformation of the tensile may cause the structural stability on the bottom layer to be more stable. So it is possible by adding more tensile and creating more force, the structural stability will become more stable.
Taking into elastic quality of the tennis ball, it might be possible, but for the theoretical model, it should not be in that way because for the 20 layer, the top 7 layer will be the same situation as the bottom 7 layer, so it should not be stable.
And that's because your analysis,
We did not take an elastic perspective into consideration.
So I agree with you on it, but I want to add on that the tennis ball, because it has tolerance, the tennis ball is different, and the higher we build up, the more torque, the deviation of the torque will be bigger. So we find in our experiment that the higher we build it, it's become more unstable and more impossible to do.
Thank you. Any questions? The juries are busy counting the points. If no more questions, you may have a seat. Thank you. One more minute. Ready? Okay. Now the points for the reporter. Okay. That's 7, 8, 7, 7, 7. Okay. Second is for the opponent. Ready? That's 8, 8, 7, 7, and 7. Now for the reviewers. 8, 9, 8, 8, 8. Okay. Thank you. Okay, so I think we only have 3 teams, so we have 15 minutes of break.